Yeah, welcome. So the topic we'll be discussing in this lecture is breadth first search. Okay. So as we have discussed already, breadth first search is similar to level order tree traversal with respect to tree traversal technique. So in graph also it is similar. We visit level wise. Okay. So first you visit all the nodes in level 1, that is V0, visit that. Then visit all the nodes in level 2, okay, from left to right, that is V1 and V2. Then visit all the nodes in level 3 from left to right, that is V3, V4, V5 and V6. So V3, V4, V5 and V6. Then visit all the nodes in level 4, okay, that is V7, right? Fine. So we are going to discuss this implementation in two ways. First is by using adjacency list alone, okay. The second method we'll be using is using adjacency list and queues. Okay. So first let us see how to implement this using adjacency list. So first you have to create adjacency list of this kind. Then it is very simple. Just in this adjacency list contains 8 pointers. Start with, that is pointer 0 to pointer 7. Start with 0th pointer and visit all the nodes that is pointed by it. 0 is pointing to first node. So first we will visit 0, okay. The root vertex first we will visit and we will display here, right. Once it is visited and displayed, we will also maintain this visit array, okay, where initially all the vertex will be mentioned as 0, which means they are not visited. After visiting 0, we will make this as 1, okay. So this we will do at the beginning. Then we will start with the 0th entry of this array of pointers, which is pointing to node 1. Check whether node 1 is visited or not. It's not visited. From this visit array, you have to check whether it is visited or not. As it is 0, it is not visited. So visit it. That is, display it and make it 1. Okay. Then from here, go to the next. That is node 2. Okay. Is it visited or not? No. So visit it. That is, display it. Then go to next null. So whenever you reach null, you have to move to the next location of the array pointer, okay. So we will start from 0th location of the pointer to the 7th location. For each pointer we will continue until null is reached. So the logic would be simple. So now come here, see 0 is visited or not. Yes, visited. So just pass on to the next link. 3 is visited or not. No. So visit it. Visit and display it. 4 is visited or not. Next. No. So visit it and display it. Okay. After 4 it is null. After 4 it is null. So go back to the next pointer, that is 2. 0 is visited or not. Yes. So next is 5. Is 5 is visited or not? No. So visit it. That is, make it 1 and display it. Then go to the next. It is 6. 6 is visited or not? No. So visit it and display it. Then go to next. It is null. It is null. So if it is null, again you have to move to the next pointer. It is 3. 3 is pointing to 1. Is it visited or not? Yes, it's already visited. So go to next. 7. 7, is it visited or not? No, it's not visited. So visit it. Okay. After 7 it is null. So go to the next pointer. By this time itself we have visited all vertex, but still you have to continue. Go to 4. Check where 4 is pointing 1. Is it visited or not? Yes, it's already visited. Go to next 7. Is it visited or not? Yes, it's already visited. Go to next null. So null means go next. So here it is 5th entry of the array of pointer. It's pointing to 2. Is it visited or not? Yes. So go to next 7. Is it visited? Yes. Go to next null. So if null is there, go to the 6th pointer entry. It is pointing to 2. Is it visited or not? Yes. And the next pointer is pointing to 7. Is it visited or not? Yes. Next is pointing to null. So null means again you have to go back to the next array entry, which is the last entry. It is pointing to 3, is it visited? Yes. Next is 4, is it visited? Yes. Next is 5, is it visited? Yes. Next is 6, is it visited? Yes. Next is null. Now you come out, is there any other array locations? No. So just stop. So this is the first method of implementing this logic. So let me show you the logic. So, so as usual, we are creating node, okay, with key and a next pointer. We are creating an array of adjacency list. There is no stacks here. There is no stack here. It's not required. Okay. We are creating a new node. Okay. But currently we are not using new node. That is for when you use with what you call queues. Okay. That is the second another style of implementing BFS. Okay. This front, rear, all these are not required. Okay. Because we are not currently going to discuss that code is here, but later I will explain that. Now coming to the actual, so this is create graph. This is the same logic which we have discussed previously for DFS for creating the adjacency list, and this display graph is to display the adjacency list. This initialize visit is used to make sure that initially visit of all vertex is initialized to 0, and this is the code for BFS. Here you can see first we are creating a pointer traverse and we are calling the function initialize visit, which makes all which makes the visit of the visit array entry to zeros. These all entries will be made to 0, uh, which means that it is what you call none of the nodes were visited. Okay, then we are using a for loop for I is equal to 0, I less than v. V contains the number of vertex I plus plus, and then we are taking one pointer traverse equal to adjacency list of I. Traverse equal to adjacency list of I. We are taking that is it is pointing to the for currently adjacency list of I is 0. So adjacency list of I means 0th is pointing to the 0th entry in the adjacency list. Okay, this one it is this one. Wherever this is pointing, there traverse will be pointing. Okay. So anyway, first we have to display 0, right? I mean the root node. So first we are checking if visit of I is equal to 0. Visit of I means initially it will be I is 0, so visit of 0, is it 0 or not? So initially all vertex will be 0, so it will be 0, so we are displaying printf percentage %di, it will print 0, and then we are making visit of I, that is visit of 0 equal to 1, which means that node is visited. Now traverse is pointing where visit of 0 is pointing. Visit of 0 is pointing to node 1. So traverse is also pointing here. Okay, so then what we are writing is while traverse not equal to null, if visit of traverse arrow key, if visit of traverse arrow key is equal to 0, then we are visiting that printf percentage %d traverse arrow key, and we are making visit of traverse arrow key equal to 1, and then traverse equal to traverse arrow next. That's it. So what it will do, so in that particular link, whatever the nodes is there, it will visit one by one until it reaches null. Okay, so it will, after visiting 0, it will visit 1 and 2. 1 and 2 will be displayed. Once it reaches null, the control will go to the for loop and I will increment. Now I will become 1. So now I points to this second one, wherever the, I mean this second entry, that is the first pointer, wherever points, there it points. Okay, so it is point, so now I is 1, so is 1 is visited, it's already visited. Okay, and that pointer where it is pointing, the one's pointer is pointing to 0, is that is visited, that is also visited. So then go next, then it will visit 3, 4, so in that order it continues. So the logic is quite straightforward. Okay, so if you want me to execute, I can execute. So the same graph. Okay, so it's the same graph. There are 8 nodes, and vertex for 0, I mean the adjacent vertex for 0 is 2. These are 1 and 2. For 1 is 3. These are 0, 3 and 4. For 2 is also 3. These are 0, 5 and 6. For 3 is all 3 is 2, these are 1 and 7. For 4 is 2, these are 1 and 7. For 5 is 2, these are 2 and 7. For 6 is 2, these are 2 and 7. For 7 is 4, these are 3, 4, 5 and 6. Okay, you can see here 0, 1, 2, 3, 4, 5, 6. That is the order, that is the level order. Okay, 0, 1, 2, 3, 4, 5, 6, 7. Okay, the last one is 7, right? Okay, so so this is nothing but the adjacency list. There are two ways of implementing. I said this is the first way of implementing. The second way of implementing the logic, let us discuss now. Okay, so in the second way of implementing, we are going to use a queue. Okay, first as usual we will display the root node. Root node is 0, that we will display. After that, what we do in the sense, whatever the root node, okay, whatever the root node, that we will push into, that we will insert into a queue. See, here we are going to use queue using linked list. Okay, because previously we discussed that if you use a queue with an array, then we face one problem, that is we will not be able to recognize whether the array is I mean whether the queue is full or empty. The condition for full and empty will become same, and we would not be able to check whether the queue is full or empty. Because of that, we went to the concept of circular queue. Okay, but if you represent queue as a linked list, then that problem will not be there. Then there will not be any problem like uh, uh, whether there will not be such problem of what you call the condition for full and empty is same. The reason is, when you use a linked list, there is nothing like full. We're getting each entry in the linked list will represent to one queue element. Okay, for a linked list you can add any number of element, so there is no condition for full, only we have a condition for empty. Okay, only we have a condition for empty, right? So what we do is, initially we set the front and the rear pointer equal to null, so we use pointers. So initially we will set the front and rear pointers as null, which means the queue is empty, right? First I'm just trying to explain how the logic works. Queue logic works with linked list. Then when one node is added, say we are adding just one node, we are inserting one node into the queue. So say let us, this is x, this x next will point to null. Okay, now front and rear both will point to this x. Front also will point to x, rear also will point to x. Are you getting? Because this is the first node and also this is the last node. Insertion will happen through the rear end, deletion will happen from the front end. Okay, now if you insert one more element into this queue, what will happen in the sense, if you insert one more element here, to this next one more element will be added. Okay, now rear will point here, no more rear is pointing here, but front is still pointing here. Okay, say this is y. Now if you add one more element, say z, okay, now rear will point here. Okay, no more rear is pointing here. Now if you add one more element, say a, now rear will point here. Are you getting? And this will be null. Okay, say you delete one element, then what will happen? If you removing or deleting always happen in the front end. If you delete this element, what will happen is just this will become the front, that's all. Okay, this will become the front. Once again if you delete, this will become the front. Now this is rear, now this is rear, right? Okay, once again if you delete, this will become front. Once again if you delete, this will become front. So whenever front is equal to rear, you can assume that if front is equal to rear and front and rear is not equal to null, then you can assume that there is only one element in the queue. Okay, so this is the basic understanding. So the code for this will be, then what would be the code for insert? Say we want to insert something into the queue, then how we will insert? So let us assume a new node is represented as nn. Okay, so nn represents the new node. Say I have a new node here, it is called as nn. How to insert this new node to the queue? just what you have to do is R will always, the rear will always point to the last node. So what you have to do is just you have to do R arrow next. That is, whatever the current nodes are, current nodes next pointer, the current nodes next pointer should point to the new node. That is NN. Okay. R arrow next will point to the new node. Okay. This is the first thing. And now this is not the rear. This is the rear. Okay. Say this is B. Now NN is the rear node. Okay, so rear R is equal to rear is equal to NN. That's all. So this is the logic for what? Insertion. This is the logic for insertion. Deletion. If you want to delete any node, then what should we do? Then what should we do in the sense? Always F will point to the front node. So we let us keep one pointer traverse. So we say that traverse is equal to F. Traverse is equal to F, which means traverse is pointing wherever F is pointing. So now traverse is also pointing to this first node. Okay, then actually first node, now this should become the first node. So what we will say, F is equal to F arrow next. That's it. So when you say F is equal to F arrow next, then no more that node is F. Previously that X is F. No more F. This is F. So now this will become F. Okay. Now you can return traverse. Normally in removing means we will return that node, right? So you can return traverse, right? Okay. So this is how we are going to implement queue using linked list. Here there is no problem. You can easily implement using linked list, and there is no question of queue getting full because we have more memory, right? So only queue will get empty. So when it will empty means you can identify when it has only one node. If F is equal to rear and F is and they are not equal to null, then there is only one node. At that time, if you increment F, okay, obviously F arrow, if you give F is equal to F arrow next, it will become null. Okay, when F becomes null, you make R also as null. That's it, right? Okay, so this is the logic. Now let us see. This is the logic for queue, implementing queue using linked list. Now let us see how this can be used to what you call. Now let us see how this can be used for uh, breadth first search. Okay, so what we do in the sense, first first we visit node 0. As usual, we visit node 0. So we display that. Okay, then this node 0 we will insert into the queue. So now queue has only one element, that is 0. Okay, queue has only one element, that is 0. Its next is pointing to null. So front is also pointing here, rear is also pointing here. Front is pointing here and rear is also pointing here. Okay, right? Now what we will do in the sense, we will remove this element from the queue. Okay, once you remove this element from the queue, what will happen? Queue becomes empty. Now both are null. Okay, both are null. F and rear both are null. But we remove this element, and after removing this element, we see where this pointer is pointing. Wherever this pointer is pointing, everything we will visit. This pointer is pointing to where? 1. Is 1 is visited or not? Not visited. So visit it. So visit it in the sense display that. 0 is already visited and displayed. So visit 1 and display. Okay. So if a node is visited for the first time, then we will add it into the queue. Okay, so add that node into the queue. So 1 will get into the queue now. So now 0 is removed. Okay, 0 only we are working. 1 will be, we just insert 1 into the queue. Its next is currently pointing to null. Now front and rear is pointing to this 1. It is not null because 1 is inserted, right? Okay. Now from 1 you uh, go to 2. Next, where 1 is pointing, you see that where 1 is pointing, it is pointing to 2. Okay, so it is pointing to 2, right? Okay, so is 2 is visited or not? No, it's not visited. So visit it. that is make it 1. Okay, sorry, it's here, depth breadth first search is here, 0 1 we have visited. Now visit 2. Okay, so whenever you visit a node for the first time, we will add it in the queue. So add 2 to the queue. So 2 will come here, 2 will come here, and 2's pointer is pointing to null. Now rear is pointing to 2, front is pointing to 1. Okay, now rear is pointing to 2, front is pointing to 1. Right? Okay, so this is the situation now. Okay, now what we will do, now go to the next. 2's next is what? Null. Right? Whenever you get a null, you have to remove one element from the queue. Okay, now 0, it means 0 is done. We are working with 0, 0 is done. Whenever you get a null, you remove the next element from the queue. Okay, so what is the next element? 1. So remove 1 from the queue. So now we have removed, this is the first element, right? Removal happens in the front end. So remove that from the queue. Okay, which means now there is only one element in the queue, that is 2, and front and rear both are pointing here. Okay, front is also pointing here and rear is also pointing here, both front and rear is pointing here. Okay, fine. So now one is this. Okay, that is this one, right? So I mean, whatever the element, you refer to that adjacency list. So adjacency list of 1 is what? This. Okay, so again we will see 1 is visited or not. It's already visited. Where 1 is pointing 0, is it visited? Yes. Go to next. 3. If it is visited, just pause on. 3, is it visited or not? No. So visit it. Change here to as 1 and display it. This is the first time 3 is getting visited, so add it in the queue. So 3 will come here. 3 will come here. Its next will be null. Okay. So now rear will be pointing to 3. No more rear is pointing to 2. Rear is pointing to 3. Okay. Fine. Again go next. What is that? 4. 4 is visited or not? No. So visit it. 1 and visit it. And this is the first time we are visiting 4, so add it to the queue. So here we will get 4. So the next element in the queue is 4. Okay, its next is pointing to null. So no more R is pointing to 3. Now R is pointing to 4. Okay, now R is pointing to 4. Right? Okay, but still we are working on node, adjacency list 1 only. Again from 4, if you go next, it is null. Whenever there is null, you should remove one element from the queue. So the first element is 2. So remove 2. So 2 will be now removed from the queue. So 2 will come here. Okay. So 2 will come here. This becomes 2. Okay. Now front is this. Front is 3, rear is 4. Okay. Now you this refers to the adjacency list. This you always remember, this is adjacency list. Okay. Whatever the value comes, that value of adjacency list. Okay, so adjacency list of 2 is what? First we will see 2 is visited or not. 2 is visited, and then 2 points to where? 0. Is it visited? Yes. 0 points to 5. Is it visited? No. So visit it. So this will become 1. Okay, and visit 5. This is the first time we are visiting 5, so add it in the queue. So here we'll get 5. Okay, and its next will point to null, and its next will point of null. Next after 5, what we have? 6. 6 is visited or not? No. So visit it. Okay, so after 5 we'll have 6. 5 will point to 6. 5 will point to 6. Okay, 6 next will point to null. Okay, right. Now after 6, what you have? Null. So whenever there is null, you have to remove. So remove 3. Remove 3. So now here we'll get 3. Here we will get 3, and now rear is pointing to 6. Front is pointing to 4. Okay. Now this is rear. Rear is pointing to node 6, the last element in the queue, and front is pointing to node 4. Okay, the first element of the queue. 3 is now we got 3. We got here. Okay. Now adjacency list of 3 is this. First we will see whether 3 is visited. Yes, visited. Where 3 is pointing 1. Is it visited? Yes. Go next. 7. Is it visited? 7 is not visited, so visit. Okay, 6 we have visited already, 7 you visit and display it, right? Okay, so 7 we are visiting for the first time, so add 7 to the queue. So 7 will come here, 7's next will point to null, 7's next will point to null, 6 next will point to 7, 6 next will point to 7. Okay, fine. Now you continue here. 7's next is what? Null. So whenever there is null, you have to pop. Okay, so 4 will come out now. So remove 4. So remove 4. So here we'll get 4. Okay, so here we'll get 4, and 4 is removed from the queue. 4 is removed from the queue. Okay, that is now front is pointing to 5. Now front is pointing to 5. Okay, so 4. So currently 4, if it is, so it means it is adjacency list of 4. So what is adjacency list of 4? Adjacency list of 4 is this particular thing. Okay, so this is pointing to node 1. Is it visited or not? Yes. 1 is pointing to 7. Is it visited or not? Yes. Next, it's null. So whenever there is null, you have to remove. So remove 5. So remove 5. So 5 will come here. So 5 will come here. Okay, which means now this is pointing to 5. Which means now this is pointing to 5. It is no more pointing to 4. Now it is pointing to 5, adjacency list of 5. Okay, and 5 is now removed from the queue. Okay, so F, now front is pointing to 6. Now front is pointing to 6. Okay, so now you see here 5, is it visited or not? Yes. Then 5 is pointing to where? 2, is it visited? Yes. 2 is pointing to 7, is it visited? Yes. 7 is pointing to null. Again null. Whenever you reach null, remove. So what is in the front of the queue? 6. So 6 will come here. So here we'll get 6. Okay, here we'll get 6, and 6 will be removed from here. 6 will be removed from here, and here we'll have only 7. Okay, so rear also points to 7. Sorry, front also points to 7, and rear also points to 7. Okay, this is front, and here we have rear also points to 7. Okay, and this is 6, it is pointing here. Okay, it's not pointing to here, right? Now what is 6? 6 is visited, yes. 6 to 2, 2 is visited, yes. 2 to 7, 7 is visited, yes. Next null. So when there is a null, you remove. So if you remove, what will happen? This will become 7. This will become 7. Okay, 7 will come here, and this is removed. Okay, this is removed. So if you remove that, now the queue is empty. Now the queue is empty. Okay, that is rear and front both will now point to null. Rear is equal to front is equal to null, because as of now the queue is empty. Okay, so now we got 7 here. Currently we got 7 here, which means it is pointing where? It is pointing to the 7th entry of the adjacent list. 7 is visited, yes. 7 is pointing to 3, is it visited? Yes. 3 is next is pointing to 4, is it visited? Yes. 4th next is pointing to 5, is it visited? Yes. 5's next is pointing to 6, is it visited? Its next is pointing to null. So when you have null, what you should do? Pop. Sorry, remove the element from the queue. Now if you remove, what you will get? You will get null. Okay, you will get null. So this is the condition to stop the process. So now when you remove, what you get? You will get null. Okay, so when you get null, you should stop, right? But already we have displayed that in the what you call BFS order. But the condition to stop is when you try to remove one element from the queue, if you get a null, then you have to stop. Okay, fine. Let us see the code. So here we are first let us see the code for the linked list representation for queue. Okay, so we are maintaining two pointers, front and rear, of type struct node. Both are assigned with null. This TOS max size, all these things are not required. Okay, we can remove this. Int v is required, this is not required. Okay, right. and this is the condition, this is the code to insert a new node. Okay, here I am passing only the key. Okay, after passing the key, with that key we create a new node. Okay, so if a insert of 0 means 0 will be passed and that will be inserted, and we'll create a new node with 0 and that will be inserted. Okay, so new node is a pointer to struct node. We are allocating space for the new node. Its key is assigned with k. Its next is assigned to null. Always new node's next will be null. Okay, then if rear is equal to null and front is equal to null means q is empty. Okay, if q is empty, then both rear and front should point to the new node, right? Because there is only one entry, so that we are doing like this. So if this is the first entry, first insertion, then first we check if rear is equal to null and front is equal to null, then rear is equal to front is equal to new node. Otherwise, if it is not the first entry, then it should be added as the last node. Okay, so last node is always pointed by rear, so rear arrow next is equal to new node, and new and rear is equal to new node. Now whatever the new node, that will become the rear. Okay, so that's it, the code for insertion. Coming to remove a particular element from the queue. So first we check whether the front is equal to null or not. Here we maintain a pointer called traverse. If front is equal to null, we return -1. Okay, so I said no null, at last it should return null, but in the coding we are using -1 instead of null because we are returning an integer. Okay, it's not a pointer. Okay, so if it is -1, then we have to stop the process. Okay, if front is equal to rear, if front is equal to rear, okay, okay, and rear is and not null, okay, that is the case. If front is equal to null, then this will happen. Okay, if front is equal to rear and both of them are not equal to what you call null, because if null means this will happen and it will return -1. So this condition will work only if it is not equal to null. Okay, if front and rear both are equal, in that case it means there is only one node in the queue. Okay, so now what we are doing, traverse equal to front, whatever there is only front will always point to the first node, so we are making traverse to point to front, and we are making both front and rear to point to null, because after removing this node there is nothing in the queue, right? Okay, fine. Else, if this condition is not satisfied, if front is not equal to rear, which means that, and also front is equal to null also we have checked already. This is to check whether the queue is empty or not. This is to check whether there is at least one node, whether there is only one node in the queue or not. If these two conditions are satisfied, then it means that there are more than one node in the, there are more than one element in the queue. Okay, then what we say, traverse equal to front. Now we are making traverse to point to the first element of the queue, and we are making front is equal to front arrow next. Okay, then we are returning traverse arrow key. We are returning only the key, not the entire node or the pointer. Okay, so the traverse can be either this traverse or this traverse, either one will execute, right? So instead of, I can also return here itself, then I have tried two return statements, one here and one here. To avoid that, a common return statement is written here, which returns traverse arrow key. Okay, so this is the same code for creating the graph, that is to create adjacency matrix, and this is the code to display the adjacency matrix, and this is to initialize visit. Initially visit of I for all the nodes were set to 0. Okay, so this is the original BFS without using queue that we have discussed. This is the code for BFS using what you call using linked, using queues, whatever you say. Okay, fine. So here we are creating a pointer traverse. Initially we are making sure that visit is made 0 for all the vertex, and then we are visiting node 0 by displaying node 0, that is the root node, and we are making visit of 0 equal to 1. And then even though you made visit 0 1, you have to insert 0 into the queue. 0th node we are inserting. For that we are passing insert of 0. Okay, see, we are passing only integer, but in the queue it will create a node and it will be inserted. Okay, then we are writing a infinite loop while 1 k is equal to remove of q. Currently there is only 0 is there, that will be removed. Okay, After removing, we check whether k is -1 or not. If it is -1, we break, because that is the condition for breaking. Otherwise, what we do, we make traverse to point to adjacency list of k. So this remove of q, it will not return the actual node pointer, it will return only 0. Okay, so adjacency list of 0 is nothing but it will refer wherever adjacency this pointer is pointing. Okay, so that we'll get, right? So traverse is pointing wherever adjacency list of 0 is pointing. Okay, traverse is pointing wherever adjacency list of 0 is pointing now. Okay, now we have to just pass on through this. We have to see whether it is visited or not. If it is not visited, visit and 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 insert that into the queue. So that logic. So first we are checking whether visit of traverse arrow key is equal to 0. If it is 0, then print that key and make that visit of traverse arrow key is equal to 1 and insert into the queue. Okay, in spite of whether it is visited or not, the traverse pointer should be incremented. If it is already visited, then just increment the traverse pointer. If it is not visited, then visit it, display it, insert into the queue, and then increment. So we keep incrementing. So like that, it will display all the nodes pointed by the adjacency list 0 until it reaches null. Once it reaches null, what will happen? It will come out of the while loop. Okay, again, what is there? It's an infinite loop, k equal to remove q. So now remove means what will come out? 1 will come out. So now we will visit all the nodes pointed by 1. Okay, and after 2 3 will be inserted, after 3 4 will be inserted. Okay, again when we reach here null, again we remove, so 2 will come out. So after 2 0 is visited, 5, then 5 will be inserted into the queue, 5 will be visited, 6 will be visited. Okay, then 6 will be inserted into the queue, then again null means again remove, so 3 will come out. So 3 is pointing to 1 which is visited, 1 is pointing to 7 which is not visited, so visit it and insert into queue. Are you getting? So now we will follow, then after reaching null, again we'll remove 4, then visit everything from 4. Actually everything is visited, but still pass through. Then 5, then go through 1 2 7, then remove 6, pass through 2 7 and null, then remove 7. Whenever you reach null, remove. So 3 visited, 4 visited, 5 visited, 6 visited, null. Now if you try to remove, it will return -1. When you return -1, you come out. Okay, so it will break, right? So that's it, the logic. Okay, so okay, so these are the two ways of implementing BFS. Okay, there are two adjacency vertex for adjacent vertex for vertex 0, which are 1 and 2, 3 for vertex 1, which are 0 3 and 4, 3 for vertex 2, which are 0 5 and 6. Enter all the adjacent 0. Okay, I missed out 0. Order has changed. Okay, let me change. So 8 2 1 2. Okay, 3 0 1 2 3 4 0 3 4. Okay, 3 0 5 6. Right, 3 2 1 and 7, 1 and 7 and 7, 4 3 4 5 6. Okay, so this is using normal method, this is using queues 0 1 2 3 4 5 6 7. Right, that's it about this topic. We'll stop here. Thank you.